We have just finished the discussion of stability for this kind of system. Just a brief recap up to now. Somebody asked me to have a recap emphasizing the last part I discussed with you the day before yesterday. And we have obtained this two ordinary differential equation system of the second order, characterized by 1, 2, 3, 4 matrices as applied to the acceleration, the state space variable, and the derivative of the state space variable. So we have a second order system consisting of two equations of the second order. So if you will to transform this system in a standard form, you probably obtain 4 first order differential equations. But we want to keep in this status of only 2 equations of the second order because we prefer to work with this matrix like mass, stiffness, aerodynamic matrix, because these metrics are related in such a way to the physics of our problem. If you go in the first order form, you probably will lost this kind of connection with the physics, okay? However, do not forget that this state space variable, W1, W2, are the state space variable here able to rebuild your solution by using this shape function like phi1 and phi2. Phi1 is the following, and phi2 is the following. Mainly the first and the second mode of vibration of the homogeneous beam, okay, as obtained by considering only the conservative force of the structural part and the inertial force, period. But we have also a damping contribution here, and we have also this aerodynamic contribution, which is actually presenting like a stiffness, but a very, very special stiffness because it is a skew-symmetric stiffness matrix in this case, okay? So we have to focus our attention on this problem. So after the physics, the transformation of the mathematical model, partial differential equation model, into an ordinary differential equation model, and then we want to study the stability of the system. This system in a standard way. And the standard way is the way for searching the exponential characteristics of this equation, which means also search the poles of the transfer function of the system. We discussed this point past time. These 2 points of view are fully equivalent. Therefore, in the case of no damping, please, first case, no damping. So we are actually avoiding the matrix applied to the velocity vector. In the case of no damping, our characteristic equation is obtained just taking the determinant of this matrix here. And the determinant here is this by this minus this by this. We have a first discussion the day before yesterday, and the discussion was the following. Imagine not to have the aerodynamic. So this capital lambda is something related to the dynamic pressure. So imagine to have zero dynamic pressure, zero damping. What happens to the structure? What about the poles? The poles are the structural poles. And if you want, in this case, discuss the stability, but not the elastic stability, the buckling stability, you can do this because we are considering only a pushing force, lateral force, and therefore this parameter, n bar parameter, can be considered also as a discussion stability parameter for the buckling stability. And the discussion is very easy to be performed because here you have the poles that are purely imaginary poles, and therefore this parameter n is able to move the imaginary part of this pulse, which is the only part present in this case for the pulse. And therefore, this means that this parameter is able to change the frequency of your system, the natural frequency of your system, keeping the mode shape the same. So we are discovering a standard results of structural analysis, which says that in the case of conservative force, the buckling phenomenon is just a reduction of the stiffness of the system, can be reduced to a reduction of the stiffness of the system. And this is what you can see here. As limit case, you have that a couple of poles converge to the origin of the axis, just like a very limited case. And this is the case of buckling with conservative force. Next, now we want to study the aeroelastic stability. So consider a lambda not equal to 0 and study this equation. Okay? So we have frozen the axial load. We are frozen we don't want to study the buckling, but we have a fixed buckling force. And the first question I want to ask is the following: is ever the instability induced by the aerodynamics might it be a static stability or not? Is there the possibility to have a static stability in this case? The answer is not. The static stability cannot occur. And why? Because the condition to have a zero pulse, the answer to the question, is there any zero pole? Is there the possibility by varying the lambda parameter to have zero pole? The answer to this question is this case can be also reached when you have a lambda equal to minus omega 1 by omega 2 to the power 2. And that means that lambda square should be a negative number in this case. So you have an imaginary value for the parameter for having this condition. And therefore, in the real world, you don't have no kind of this instability, but please remember, by considering this mathematical model, so this mathematical model is not able to give you a static stability for the panel flutter. The only possibility for having an instability is an oscillation. So a couple of poles crossing, a couple of complex conjugated poles crossing the imaginary axis. For this way, we can talk about flutter, panel flutter, and not divergence panel. Okay? And this is interesting because this is the base concept of flapping flag. When you see a flap, when you see a flag, when you see a flat surface, very flexible, like a flag or like a membrane, and you have a wind, you probably don't have something like just like a static stability. You should have almost always oscillation. Okay? And this is an important result we have found. And now we want to study this kind of instability in deep. How? Okay, so we want to solve this equation, and we can't, in the general case, we have to find the solution, but in particular, this is a biquadratic equation, as you can see. So you can find the square of the poles as equal to, and you can apply the standard formula for second order equation, like minus omega 1 square omega 2 square by 2 plus minus square root of omega 1 square plus omega 2 square by 2 minus omega 1 square, omega 2 square minus lambda square. Okay, now we can just rewrite this in a more suitable form like this. Keep this coefficient, this first term, and then here we can write, if you consider this term, if you consider this term here, if you consider this term here and this term here, and you develop, I'm sorry, here I have forget a square. Okay, if you develop this binomial to the power 2, the crossing product, the double crossing product can be simplified. Consider these two at the denominator, please. You can combine the crossing product with this omega 1 square, omega 2 square. So at the end of the story, you can compact these two terms like the omega 1 square minus omega 2 square divided by 2 to the power 2. This is very algebra, linear algebra, minus omega square. So a third discussion that I have is the discussion on not the poles, but the square of the poles. So imagine to have a plane with the real part of the square of the root and the imaginary part of the square of our root. So this solution here. Okay, for lambda equal to 0, you have two negative solutions. You have, for lambda equal to 0, you have minus omega 1 square plus omega 2 square with the minus sign divided by 2, and you have plus minus only this, and so you have omega 1 square minus omega 2 square by 2. And if you take the double combination of the sign, you have essentially two sources of your root locus, one root here and another root here, like minus omega 2 square, a real number, so in the real imaginary axis, and the other one in minus 1 square. So these two cross are the first value for S square, Then you want to move your parameter lambda by increasing and increasing lambda, and what happens? What about this quantity? This quantity is the average of these two numbers. So this quantity here is here in the middle. Okay? Is here in the middle. Here in the middle, you have minus omega 1 square plus omega 2 square by 2, the average between minus omega 2 square and by minus 1 square. So if you look the standard formula for the second order equation, you have that the two solutions are the mean value plus a quantity minus a quantity. So if you increase lambda, you are currently increasing, you have this average value, and you are adding and subtracting a standard part. And this part is growing and is for lambda is equal to 0, give you this root, this and this. But when you increase lambda, this quantity is less and less and less, and therefore your two roots are currently and symmetrically moving in this way. Okay? So you are, for lambda equal to 0, you have a root here, and then this root moves toward this average point. We are describing the root locus in lambda, And for a special value of lambda, you have that the two s square root are coalescing in the average value. And this occurs when the square root is 0. So you have a critical value for lambda square, which is a coalescence value, which is equal to, for lambda equal to minus omega 1 square plus omega, excuse me, for lambda equal to this value here, cancelling the root square. So for lambda square equal to omega 1, excuse me. This is for lambda cancelling this argument of the root. So for lambda equal to omega 1 square minus omega 2 square by 2 to the power 2. So for zero value of our dynamic pressure, we have in the s square plane there are two negative roots. If you increase lambda, these negative values are currently converging to the average value up to a coalescence. And the coalescence is a special value for lambda. I call this critical coalescence. I don't know. And what happens after? After this value, you have that the argument of the root square becomes negative. So the part which is add and subtracted for obtaining the roots becomes imaginary. So you have a complex number with a fixed real part and with an imaginary part which is increasing as positive, and symmetrically is decreasing as negative. So the final result, in my opinion, is the following. You have a straight line here with the poles of the s square, do not forget, are going up here and down here. So this is the situation. In the negative axis, you have this closer and closer and closer coalescence, and then something like this. Very simple. Let me recap this in this new slide. We have in the s square plane the following. We have the real part s square, the imaginary part of s square, something like this. We have from here, we have from here to here, we have this in the average, and then this lambda value, critical or lambda coalescence value, the power 2, is equal here to the difference minus 2, the difference divided by 2, and then to the power 2. Okay? Now, what happens here in the true S plane? The true plane is the plane where we can find the root of the 4 roots of our polynomial. We have only 2 roots in the S square plane. We have, of course, 4 roots in the real plane with the real part of S and imaginary part of S. I'm sorry, but I'm fighting with this system. Can you see my, please say yes if you can see my whiteboard.
Yes.
Okay, thank you. So, imaginary S, not S square. Now we have to discuss about how can we get the square root of a complex number. Do you know this story? What about the square root of zeta, which is equal to w with w and zeta complex number? Imagine to have w. In this part here you have w as s squared. In this part here you have zeta to be calculated. When you have w, the rule is the following. In the complex number, the complex plane, excuse me, and if this is w with the real part and imaginary part, or better, if this is the amplitude of this number, rho, and this is the phase of this number, we have to consider the Mohr formula. So this number w is represented by rho by e to the power j phi. And what about zeta? Excuse me, I'm very sorry. I have to talk about zeta, no? And this is zeta, and this is, excuse me. I have inverted the order, and I'm very sorry. Because zeta is the number to be rooted. And w is the result of the root square operation. Okay? So this is w, this is not w, this is zeta. And therefore I have that this is zeta in this form, so this is rho of zeta, and this is the phase of zeta. Okay? Okay, so if this is w, what about, excuse me, if this is zeta, what about w? W is a number such that the amplitude of w is the nth root of the amplitude of zeta. This is the first point. M is the order of the root square. Okay? And what about the phase? Well, we have not only one determination for the phase, but we have many determination of the phase. And the number of this determination is equal to the number n. So, the first determination for the phase of the w, of the number w, the first one, can be obtained just taking the phase of the number zeta, and then you have just to divide phi zeta by n. Okay? And what about the other? The other n minus 1 determination are on a circle of radius equal to r, w, and all equidistant. Okay? Consider an example here for a cubic root, n equal 3. Okay? For n equal 3, an example, you have this original number, like this, and this is rho W, excuse me, rho zeta. So take the cubic root of this number, and I show you the result in green. So this is rho W is equal to cubic root of rho zeta, and this is the first. This is not the first determination. Now you have to divide this phase angle by 3 and take 1/3. So take 1/3 of this phase angle like this, and this phase is phi W1 equal to phi zeta divided by 3. Okay, so this here is the first square root determination. And what about the other? The other two? The other two are in this circle. Excuse me. Consider this circle. Do this figure better. So in this circle, you have this as a first. So take the other two, considering 120-degree angle. And the other root are one here and one here. So this green cross quantity are the result of the cubic root as applied to a complex number. Okay? Okay, but here we have a square root. So let's apply together this formula to our exercise here for n equal to. Okay? And start by the root of the source of the root. So for example, what about this point and this point, which are minus omega 2 squared, and this which is minus 1 square? What about here? We know this result because we have to take the root square of a negative number. So you have a plus j and minus j omega 1, as you know. But you can apply this rho because you have an amplitude of this number. You have an amplitude. So the result is a number having the root square of the amplitude. So the root square of omega square is omega. And the phase, you have to take the phase of this angle here. Look, this angle phase is pi. And therefore you have the first solution with the phase equal to pi by 2. So the first root is here, because this is pi by 2, and here I have plus omega j omega 1. Okay? And you know this result is standard. The other root has the same amplitude, but there is a circle dividing the circle in two parts. Okay? So this discussion is trivial because we know what happens when you have a negative number and you have to take the square root. And this is easy to apply up to this correlation point because you have another root here, and so the other root is minus j omega 1, and if you increase lambda higher and higher, this root is going toward the average value, and therefore this is going here and this is going here, closer and closer to the origin. But after the collections point is here, and in the collections point you have that a very singular situation with the imaginary part of zeta being equal to 0. So you have, in the collection point, you have this, that these two roots are currently going here. I have written the situation for minus omega 1 square, but we have the same for, of course, for minus, I have do a very relevant error, excuse me. The other root are 1 here plus j omega 2, and the other is here, minus j omega 2, okay? And we are currently taking the square root of this number and the square root of this other number, okay? Whenever lambda is increasing, the amplitude of omega 2 is decreasing, and the amplitude of omega 1 minus is increasing. And therefore, what happens, excuse me, I was wrong before, I'm sorry. What is happening is that this is going higher and higher with the same phase equal to pi 2. This is higher and higher negatively with a phase equal to minus pi 2. But the other root, the omega 2, is giving this with a value less and less in amplitude, and this here less and less a negative number as imaginary part. So we have a couple of roots which are going closer and closer, okay? And this is due to the fact that this is lower and this is increasing, and correspondingly this is going down, going up, going down, and going up, okay? At the end of this, when you are here in this collections point, what happens in the collections point? In the collections point, the imaginary part here, this part here is cancelling, and this argument of the root becomes negative. So after an epsilon value of lambda further with respect to the critical value, this root became imaginary, plus an imaginary part minus an imaginary part. And therefore here you have that an imaginary part means that this part here became imaginary in the S square plane together. Pay attention. So you have this imaginary part on the S square plane. But what happens corresponding to the S plane? Okay, so now we are studying this position here and this position here. After this, we want to study this complex number here. What happens to this complex number here? You have this complex number. And what about the phase of this complex number? This is the phase of this complex number. Okay? And you have to divide this phase by 2. Dividing this phase by 2, you have a phase angle less than pi by 2. Okay? And this is the first determination. This means that after the collections point here, you have a root with a modulus which is higher with respect to the modulus of the collections, but the phase is a phase which is a phase less than pi by 2. And therefore, you should be here. You should be here in the right part. But this is not the only root. You have this root, here, but you have also this root here. Okay? And what about the phase of this angle? The phase of this angle is a phase of angle which is excuse me, I'm doing confusion. I'm very sorry for this. I'm very sorry. Start by this. Excuse me. I'm sorry. So this is the complex number. This is the modulo the phase of this complex number. For having the square root, I have to divide this phase by 2. Okay? So take this, divide it by 2, and you have this first determination. First determination for the square root. An angle less than pi by 2, this angle here. The other one is such that the circle is divided by 2 equal k slice. So you have another solution here. So the two final phase are one for this complex number, another one for this complex number. So taking the square root of this value, you have a solution here. I'm sorry for this, guys, excuse me. You have a solution here, and the other solution here, corresponding to this and this. Okay? Okay, this is this pole here. The other pole here, the other s squared pole here, is another complex number. You have to take the square root, and therefore you have to take this phase divided by 2, and therefore you have this value, dividing this phase by 2, and so you have this solution and the other solution here in the opposite side of the circle. And so you have this here and this here. At the end of the story, your root locus is composed by these two branches, and you have a starting port here going down, a starting port here going up, a coalescence, one in the right hand side and one in the left hand side, and the same picture down here in the negative part of imaginary axis is a specular. It's just like a mirror. So you have at the end this situation. I have this situation here. I want to recap for you this situation in this new slide. And we have finally in the real S and imaginary S the following. Start plus j omega 1 plus j omega 2 minus j omega 1 minus j omega 2, and then go down, go up, down, hit the coalescence, and then here and here, and the same here, go, and then right hand side, left hand side here. Okay? So, for this special case of instability, you have the crossing of the imaginary axis in a very, very special way. It's not a direct crossing, it's a crossing characterized by a coalescence before and then a crossing. This is very unusual. It's not the standard case, absolutely. But this is typical of such a kind of system without damping. For such kind of a characteristic equation, we have a characteristic equation which is a biquadratic equation for the poles. Okay? So I want to emphasize this point. This is not standard. This is standard. This is standard in the life. Okay? And this is the crossing. But this is not standard. Coalescence and then, okay? But we have encountered this kind of instability for this special. And therefore, what we have called like a critical value for lambda, also known as a coalescence value of lambda, is also the flatter value for lambda. Because it's the critical value of the parameter such that after, for values higher with respect to this parameter, we have a complex conjugate of pole with positive real part. And so this is the flatter limit value in our case. So this flatter limit case is just this quantity here, okay? And you can see that in this case, this quantity is just an average it's not an average, is omega 2 minus omega 1 to the power 2 divided by 2, and this is the critical value of our discussion. Okay? So in this case, the coalescence of the occurrence of the coalescence of the root is also the occurrence of instability. Okay? Now, let me introduce the more general cases of damped system. In the damped case, we have the following characteristic equation. We have this, note that also in this case the structural oscillators associated to our system are quite independent. If you put lambda equal to 0, again, we have damped system separated. So we can determine the poles by imposing to this determinant be 0. And this is the novelty. The novelty is given by the damping part, as given here by the term we have not considered, this term here, in time domain. Okay? This is the damping. Okay. And what happens in the case of damping? We can study the characteristic equation, and we have the following fourth order polynomial. We have s squared plus zeta 1s plus omega 1 squared by s squared plus zeta 2 s plus omega 2 squared and we have plus lambda square equal to 0. Okay? We can develop this this fourth order equation, and we have s squared to the power 4. We have also a third order term given by zeta 1 plus zeta 2 third, as you can see easily, developing this product. So we have s cubed here. We have the second order term as given by this contribution, which is the natural frequency of the system. But we have also this contribution by this product here. By s to the power 2, and we have the term in s, which is excuse me, which is given by developing this, is given by zeta 1 omega 1 square, omega 2 square, excuse me, because we have to cross product this by this, and we have zeta 2 by omega 1 square multiplied by s, excuse me, this is the s square, this is the s square term, not s square, and we have finally the non-term not dependent by, not multiplying s power, which is omega 1 square plus omega 2 square plus omega square equal to 0. The damping, the term of the force depending by the velocity, are not able to affect the static stability. So also the damping effect, the static stability cannot occur again, because this term is not influenced by zeta. Okay? No possibility of static stability without damping and with damping as well. Okay? So this is the final characteristic equation, and now we have to discuss the root of this quantity, and now we have a complete fourth order equation, not a biquadratic equation. This is a point, and note that for lambda equal to 0, we have that we can separate the root in the sense that we can solve separately. This quantity has to be equal to 0 and this quantity has to be equal to 0, and therefore we have that in the case of lambda equal to 0, we have that Si for I equal 1 and 2 is equal to minus zeta I by 2 plus minus square root of zeta 1 square by 4 minus omega I square. Typically, this omega 1 square is higher with respect to the square of the damping coefficient, and therefore one suspects that this quantity inside the root square is a negative quantity, and therefore I am discussing lambda equal to 0, do not forget, not thermodynamic. I am discussing this. So, not thermodynamic, but with damping, we have this, and therefore we have minus zeta 1 by 2 plus minus j square root omega I square minus zeta square I by 4. And this means that at the beginning of the story, here in our complex plane, at the beginning, we have two root but with a negative real part, one here and the other here, and one here, and another here. And this value, this distance, is a negative number equal to minus zeta 1 by 2. So our root locus now is actually starting with stable 4 poles, not marginal like before. Okay, so this means that when you have now no aerodynamics, you have a damping effect given by the structure. Okay? Okay, and what about next? For lambda not equal to 0, eventually for lambda greater than 0. Well, what I'm proposing is a standard method for discussing the criticity of our system. Okay, it's time. R5 past 3. So I propose to have a break before discussing the damped stability. And if you have a question, I have a break now of a few minutes. In the next hour, we will complete the study of the stability, considering also this case of damped solution. Damped in the sense of the panel. In the panel description, I am including the damping given by the structures and the damping given also by the aerodynamic. Okay? So I have a break.
Professor?
Yeah?
So if we wanna plot the real part versus the parameter, we see a bifurcation, isn't it?
No. Don't say the word bifurcation if you are talking about a linear system. It's forbidden. You can't use bifurcation. You can't talk about bifurcation if